Thank you, everyone. I'm Ethan Heilman. I'm going to be talking about OPCAT. One of the reasons I'm going to be talking to you about OPCAT is I'm one of the authors on BIP 347, which is the BIP to propose OPCAT. My co-author, Armin, is here right now. And I'm going to be talking about, I'm going to provide background on OPCAT, Bitcoin script, do a little bit of like Bitcoin feline archaeology to ask why it was removed. Going to discuss how we're bringing CAT back, and most of the talk will be on why CAT's valuable, and sort of like how to think about it, how to think about the risks. My talk's going to be a little bit shorter. So there'll be lots of time for questions. So if you have questions, think of them and ask me the questions. So this is probably a reminder for many people, but I just want to do a brief overview of how Bitcoin script works. So when you want to spend the output of a Bitcoin transaction, the rules which enforce whether that output can be spent or not use a stack-based language. So for example, here is a program in Bitcoin script. This program pushes 7, then it does add, it does a duplicate, and then it does a SHA-256. So what does this look like? Well, if we start with a stack, and Bitcoin is a stack-based language, very similar to Forth, when we do the push, that just pushes a 7 on the top of the stack. Everything else moves down the stack. When we do an add, it takes the top 2 stack elements, adds them together, and then pushes the result on the top of the stack. Duplicate just duplicates whatever is on the stack. So now you have 2. SHA will just take whatever's on the stack and run it through, SHA-256 or SHA-1. I guess in this case, SHA-256. So what is OPCAT? Well, the cat is actually short for concatenate. So it's an opcode which pops the top 2 elements off the stack, concatenates the 2 elements together, and then pushes the combined element on the stack. It's incredibly simple. So if we have a stack here, cat takes the top 2 elements, which would be AAA and ZZ, essentially just deleting the comma here, and pushes this back on the stack. So what's the history of OPCAT? CAT was actually, as an opcode, was in the first commit of Bitcoin. You can see it here. The next time it was changed was in 2010, where there was this limit put here, which prevented you from pushing to concatenate things larger than 5,000 bytes. And then a little bit while afterwards, there was this very well-named commit, miscellaneous changes, which removed, which first made the stack limit for CAT to 520 bytes, which is what is the stack element limit, the size of elements on Bitcoin stack today. And then it disabled 15 opcodes, including OPCAT. This is probably like one of the more important commits that have occurred in Bitcoin history. It disabled 15 opcodes, including CAT. It changed the max stack element size from 5,000 bytes to 520 bytes. And it is kind of a little bit of a mystery to me about why it's 520. The math opcodes in Bitcoin used to actually be big num opcodes that could operate on 5,000 bytes. And this changes them to only operate on 4 bytes. And it just removes like all of these opcodes and then redefines all of the math opcodes. Massive change. So why was OPCAT disabled in this? And the answer is that we don't know. There's sort of folklore that it was about opdupe, that you could do OPCAT opdupe bomb. But if you go back here, we had already limited the stack to 5,000 bytes, so who cares? And then this one limited it to 520 bytes in the same commit that removed it. So the OPCAT opdupe bomb was not actually a reason that opcat was removed. I have a little bit of a theory, but I don't actually know whether this theory is correct. So probably the reason that this commit was done was that one of the opcodes, op left shift, appears to just cause like random crashes, which means that like no one had tested it up to this point. It was just there, and if you put it on there, it would like crash on your computer. And so my theory is that there was just a bunch of opcodes that have been added that no one had ever tested or used. And they just panicked and were like, well, okay, any opcode that like we don't think anybody's using right now, we'll just remove because, you know, this is really bad. But that's just a pure supposition on my part. I have no information. I'd love to hear the story. I know someone was actually looking at trying to replicate what the left shift bug is, because I've never seen any like write-up of how it worked and why it has the properties that it claims to have had. It's probably an OpenSSL thing with a really old version of OpenSSL. So we want to bring cat back. Me and Armin wrote BIP 347, which is our proposal to reactivate cat. It would only be activated in TapScript. So when we say bring it back, we're not activating it in pre-TapScript. The pre-TapScript remains unchanged. It would be activated in TapScript using the mechanism that was designed in TapScript to make it much easier to add opcodes, which is the op success mechanism. So this would be a nice like sort of test of op success as a way of adding new opcodes. One of the reasons we actually waited to do TapScript or to do opcat now, because I've been talking about this since about 2015, is because of this op success. Makes it much easier, much nicer, much better to reason about. And we are using the same opcode that was the original opcat, but op success 126. And if you look at it, like cat is just such a simple thing to do, removing the comma. So this was the original cat code, and this is the new code. Other than a little bit of savings for how you insert it by extending the buffer, and rather than just returning false, it throws an error message. It's pretty much the same code. So where are we now? So we did a mailing list post. There was a lot of discussion. We did an Inquisition implementation. We submitted a BIP. Inquisition also has this standard system similar to BIPs. Did a Bitcoin Core club review. The Inquisition PR was merged. We were assigned BIP for 347. And it was activated on Bitcoin Inquisition. People have been using it a whole bunch on Bitcoin Inquisition. And then there was a mainnet PR, which Armin did most of the work writing. We wrote some really nice tests with that too. And the sort of, okay, so when do we do it? And this really depends on community consensus. Like I'm not the boss of Bitcoin. No one's the boss of Bitcoin. So it's really hard to say, maybe sometime soon, maybe a decade from now. I feel like it's such an important and fundamental opcode that'll happen eventually on a timescale long enough. It's just a question of the order of magnitude. So why cat, right? So there's a bunch of neat stuff you can do with cat. Really surprising. I did not realize many of these things a year or two ago. I just know that every time I was working on scripts or building protocols in Bitcoin or thinking about L2s, I would just always be like, but I really want this cat functionality. Like whatever I was trying to do, I would like hit that wall. So cat lets you do general computation. You can do vaults. You can do covenants. Even covenant proposals. Like if we got a covenant opcode, you would want opcat in addition to do much for the sort of enforcement logic. So cat's just an extremely useful opcode that lets you build a lot of stuff. It provides a path to increases in scalability and privacy. A lot of the ZK roll-up approaches can use cat to basically do cross-input signature aggregation, but at like the roll-up level. So you just suck out all the signatures. You can suck out all the inputs, and you can do, you can increase Bitcoin scale. And then the rollups could kind of function as giant coin joins. So you'd also increase the privacy. But I'm actually not going to talk about that. That's a much larger talk. So why is opcat so powerful? How does it it's such a simple thing. How does it enable this? And the way it does this is that it solves the silo problem in Bitcoin script, which is that for stack elements larger than 32 bits, they're almost always siloed to each other. So you have SHA-256 as an opcode in Bitcoin script, and you can take a value and you can compute the SHA-256 version, SHA-256 of that value. And you can do that from another value. But these two values can never influence each other. You can hash the same value a bunch of times, but A can never influence B. You can't do something like SHA-256 A comma B or A concatenated B. And this is actually what really makes it hard to do things in Bitcoin script. If they could influence each other, you could do covenants, zero knowledge proofs, a whole bunch more. And cat breaks this silo because you could just cat two values together, and now you can do SHA-256, or you can build Merkle trees, you can build signatures from elements. And this is sort of the essential power of cat. But I'm going to tell you a secret. Cat isn't really special. It's not that the cat functionality gets you this. In fact, many different opcodes and proposed opcodes get you this. Op substring, equivalent to opcat. Op-and, which was an opcode that used to exist where you could and large byte sequences in Bitcoin, gets you the same thing. SHA-256 stream, depending on how you interpret it, gets you that. The op ZKPs, any sort of Merkle tree opcode would get you this. Math opcodes, if you expanded them beyond 32 bytes. All of these both let you build cat, and you could build cat from them. They're all sort of equivalent. So the reason that I like cat rather than many of these other ones is just, and I sat down, I was like thinking about this a long time ago. I was like, I want this functionality. What's the simplest thing that lets me do it? And cat is just the most simple one that lets you do this. It's not that cat is special in its functionality. It's that cat is special in its implementation simplicity. So like, big dumb math codes, you could build opcat out of, but you got to worry about validation cost being proportional to transaction size. Substring is almost as simple as cat. Like, it's like, one or two lines more complex. So I don't think it's like a strong argument for cat or substring, but it's just like you have two things and one is just slightly less complex. You just choose the slightly less complex one. And is actually, if you look at the original Bitcoin code, is slightly more simple than opcat. But it actually using it for most of the things that people want to use in scripts would require like a number of other opcodes, and it would be like slightly more complex. But I can see an argument for and on a simplicity of implementation. But cat is also extremely simple. So cat is simple in logic and hits these immediate use cases. One of the things that's often brought up is, what about the complexity of reasoning about what cat allows? That's true. But all the other opcodes that can build cat are also sort of equal in this regard. Like, it's really hard. I think, Jeremy did an excellent job in designing opctv because it doesn't let you build cat, but like almost everything else does. Like, it's really hard to build something that doesn't let you do cat because it's just such a basic part of any programming language. So there's two perspectives. Maybe these are caricatures, but there's two perspectives I hear on how opcode should work in Bitcoin. And I think they're actually, like, in some sense, both right. You want opcodes that do both of these things. The first one is that opcode should be monolithic. They're dedicated opcodes. You predetermine the use case. The opcodes are designed to prevent off-label use. You can only use them for that. And they must fully perform that job. So like opcheck multisig, check sequence verify. They're like, they're like They're like a post hole digger. You dig post holes with them. The other perspective is that opcodes should be simple and modular, like Legos. They're not designed with predetermined use cases. They're sort of just like unleash developers. We don't know what you could build with them. This is things like op-ed, op equals, like how do you predetermine the use cases of op equals? And I really like this because I feel like there's always this, when you're like thinking about something, there's like, you only see the next hill, but when you get to that hill, you see beyond that. And then when you get to the next hill, you see beyond that. But if you started from where you began and then tried to plan out everything, you make very little progress. So I really like the idea of simple and modular opcodes. It's a philosophical difference, but I would point out that Bitcoin has both of these types of opcodes, and they're both valuable. I was very much inspired by the Unix philosophy, which is that rather than monolithic software, you build tools that in combination get a job done rather than doing it by hand in some sort of monolithic program. And the hilarious thing is I went to go look this up because I wanted to cite it in the BIP. And the example they use is cat, the cat Unix utility for concatenate. It's like, it's the ultimate sort of modular, you basically need it. It's your screwdriver in your toolbox. 1983. So the other problem with the monolithic view, and I think the monolithic view is 100% correct for certain opcodes, you want to build them that way. It's just really hard to prevent off-label uses. You can make them more expensive to use, but like, people figure out ways to use them in an off-label manner. So like we recently published this paper, Collider Script. It costs millions of dollars to spend things with Collider Script, but creating the outputs is cheap. The way it works actually is that it like gets you opcat under the hood and then uses that to build covenants. And it works with Bitcoin today. If you wanted to spend tens of millions of dollars, well, you could produce these outputs, and then if you wanted to spend them. But there's also this really cool work, which I believe there's a session on today, and also Jeremy talked about, where you use functional encryption to do covenants and this sort of behavior. And there's a implementation which I still don't understand that supposedly proposes a instantiation of this. So it's like, I feel like the monolithic perspective is it's just really hard to actually prevent these sorts of things. Instead, I think what you get is a spectrum. You have things that are like very low cost to use, like dedicated opcodes. And cat covenants are pretty cheap to use. And then you have things of moderate cost. Like if you did a zero knowledge proof with ZKPs, you want to do a ZK rollup and get like 10x scalability on Bitcoin, you're going to pay for it. And then you have things like Collider Script. So I think the right way of thinking about controlling behavior on Bitcoin is this sort of cost slider, how cheap you make it. And I would argue that this is actually an advantage of Bitcoin, or an advantage of cat. Cat is master of one trade and jack of all. So you can use cat for a lot of different things, and it isn't efficient for many of them. What cat is best at, surprisingly, is concatenating elements together. And this is very, very useful. You're building covenants, you're going to want to concatenate things. You're building Merkle trees. Even if you have a Merkle tree opcode, you're like, well, I want this byte, and then we'll plug it into the Merkle tree. So cat is excellent at this. There's probably no better opcode at concatenating things than cat, because that's what it's designed to do. Cat-based covenants, they're pretty large. They're tricky to write. There's a lot of footguns there. Cat-based starks and snarks are very large and complex. I think this is an advantage of cat because it gets us that cost spectrum. For instance, because cat isn't a dedicated covenant opcode, no one's gonna be like, oh, we have cat, we shouldn't do CTV, or we shouldn't do TX hash. You're still gonna wanna do that. But probably we only get one shot at a covenant opcode. Like Why? Because I think that human beings are very unwilling to admit mistakes. It is just pure supposition on my part. So that when we like do something, we kind of like think like, but that makes it, we backfill the reasonings for it. But I think also it's just like, we're going to use like 2 opcodes to have one. Like maybe if they don't collide with each other. But I think like patching an opcode, I don't know. My personal feeling, can't predict the future. We probably have only one shot over the short term to do a covenant opcode. Once we have that, we have to live with it. It is. But with cat, this isn't the case. You could do cat. You can see how people build these covenants, what use cases get investment in those use cases, because people aren't like, well, I want to do a company that does covenants, but like, you know, are the investors going to give me money if there's never a covenant opcode? But if you get cat, it's like, okay, we can do this. We can get these use cases out there, and then we can do a covenant opcode. I think also, like, I personally would love to see a covenant opcode like opctv alongside cat. I don't think cat's a reason. I think the value of cat is not a reason not to do a covenant opcode. But it does let you do covenant things. And the same thing's true with like a ZKP opcode. You know, like imagine I was standing here attempting to convince you for op ZKP, and everyone would have questions about like, well, do you want to use this curve, and what are the assumptions, and like, how do we know that someone can't do a DDoS, and how do we know that the code doesn't have implementation bugs in it, and like all of these sorts of questions. What if someone comes out with a better ZKP tomorrow, and then we all look like fools for adopting it? And because cat doesn't commit to any of this, it lets us experiment. And it also sort of limits the potential damage, because it's actually pretty expensive to use cat for general purpose computation. It sits at that sweet spot that lets us get our feet wet, or like lets us get over that first hill without having to plan out the entire journey. So that is my talk. My talk's a little bit short. I really want to have time for questions. How much time do I have? You got 3 minutes. All right. So my talk was a little bit longer than I thought it would be.
It's lunch next, so if you want to stick around.
Oh, yeah.
So it's Steve. Yeah.
Thanks. Thanks for the presentation. I have a question really about the last point you made. Is there data or analysis on exactly how much more expensive it is versus some of the more optimized opcodes? And then just sort of the economic, like, will we actually be able to experiment with useful services if it's too expensive?
So if I understand the question, it's how expensive is this, and where is that? Like, is it at the optimal point of the trade-off? You could imagine you'd want OpCat to be a little bit more expensive or a little bit cheaper. The answer to that is I don't know. I think for many of these things like covenants, it's cheap enough that you definitely have experiments. I think with zero-knowledge proofs, because you can use them to do transaction compression and bundle lots of transactions in there, it probably is cheap enough. I also think we're making a lot of like progress in that area, and there's a whole set of trade-offs. But there could totally be use cases for which it is too expensive, and CAT does not cover that use case.
I just love to see numbers. I don't know if I've got some. So yeah, I'll wait for you.
I'll bring it back. Okay. And Rusty should have some new numbers too this afternoon.
Yeah.
So one anecdotal case, right? Like there's a vault that some handsome genius implemented using OpCat, and the most expensive transaction in it ends up being around 320 VBytes. So that's bigger than if you had like OpVault or you had a more specialized opcode for it, but it's still within the range of practical for if somebody wants to pay for that use case, they can. It's not, you know, you got to pay for 4 megabytes of script or something.
Thanks. We go to Peter next.
So I actually mentioned this issue of cost in my L2 blog post. And something I didn't realize until I thought about more carefully is that for the Covenant use case, where you're basically building up a transaction on the stack, hashing it, and then comparing it to the spending transaction, in most cases, this is much cheaper than you would expect because you are using witness space, which has the discount, to then compare to non-witness space, which doesn't. So very roughly speaking, you're going to end up spending something like 25% more fees to build up that copy on the stack versus what fees you're paying for the non-witness space. And along these lines, I also got to point out, I mean, opcat and opctv, that's, your obvious way to go do this. You build up something on the stack, hash it, and then just feed that digest into CTV.
Yeah, I think if I understood your last point, which is the use of opcat within opctv, and like opctv, I think mentions like opcat like 9 times, and I think just ignoring everything else you can do with opcat. If we get a covenant opcode, we probably will want opcat anyways, just for manipulating stack data.
So I just wanted to ask, you touched on that we probably get one good shot at doing covenants the right way. Do you think that potentially the increased cost of working with CAT incentivizes us to do later covenant upgrades and incentivizes us to do it right with the elders out of the building now that we don't have a lead maintainer?
So your first question is, do I think that getting opcat in would make it more likely we would get a covenant in opcode? Is that correct?
Adding this new covenant opcode saves in amount, and it's a desired use case because it enables some L2 rollup or something that people like.
Yeah, I mean, I definitely think that getting opcat makes, like if I had my druthers and I was the boss of Bitcoin, which I am in no way the boss of Bitcoin, no one is, I would be like, let's do opcat and a covenant opcode. But I recognize that there's it's really, really hard to change Bitcoin. And opcat seems like the simplest thing that we can get that like gets us a little bit further to building confidence that we could do that we could get a covenant opcode. So I think like in that environment, I believe opcat makes the case easier for a covenant opcode. If someone really doesn't want a covenant opcode, I can see the argument of like, well, we have to stop it at opcat because then when people are using this use case, the lower cost will be compelling enough that people will now want a covenant opcode.
I mean, I'll point out, I'd go argue the other way because CTV makes so much sense with opcat. CTV is your obvious covenant opcode that gets us covenants, and then CAT is more, well, now that you've had simple covenants, do we really want all the complex stuff? And if you do, then CAT's your obvious choice. But these are, I think, two separate issues.
I totally agree. And I think it comes down to like, I don't have like a crystal ball, but I do think that if we got CTV, it would make it more likely that we would get CAT. And I think that if we got CAT, it would be more likely that we'd get CTV, but that's just my like unscientific supposition.
Why not both?
Why not? That would be my ideal world, but
What's the likelihood of that happening in the same upgrade?
I have no idea. And like that really is just the community has to decide what they want.
We need clairvoyance here. We need,
yeah, well, you bring in a medium, and we can find this out. But I do not pretend to see the future. No.
All right, Ethan, thank you so much. Appreciate it.